All right, in this video, I'm going to continue on from what we just did, which was finding the derivatives of the 6 trig functions, and now we're going to use those in these examples. So the first example, we have y equals tangent of x minus 5x squared plus 12x sine of x. So y prime is equal to, since we have 3 terms, we're just going to take the derivative of each term. So the derivative of tangent of x is secant squared of x minus 5x squared. So that's using the power rule. So that'll be negative 10x. And then plus, here I have 2 terms, or I'm sorry, 2 factors that are getting multiplied together. So we're going to use the product rule. Remember, the product rule just says the derivative of the first times the second plus the first times the derivative of the second. The derivative of sine of x is cosine of x. So we can leave it like that, or we could do a little cleanup here. Secant squared x minus 10x. Actually, there's no cleanup we can do except for getting rid of those square brackets. Okay, so there's the first one. The second one, we have f of x equals 3 secant of x minus 5 thirds, or 5 over 3x to the 7th. Before I take the derivative, I'm just going to change that fraction there to 5 thirds x to the negative 7th. Now, if I didn't do that, we would have to use the product rule for that fraction because the x would be in the denominator. But if we move that factor to the numerator, then we can use the power rule. So the derivative of 3 secant of x, so that's going to be 3 times the derivative of secant of x is tangent x secant x minus, now I'm going to use the power rule. Negative 7 gets multiplied by the coefficient, which is 5 thirds. So negative 7 times negative 5 thirds will be plus 35 thirds x, and then I raise that, or I change that power, I lower it by 1, so it becomes negative 8. So you could leave it like this, or if you, tangent x, secant x, if you don't like negative exponents, you could write this as 35 over 3x to the 8th. All right, the next one, number 3, we have g of x equals 5x cubed plus cosecant of x. So g prime of x will be, again, power rule, 5 times 3 is 15, x squared. The derivative of cosecant of x, well, that's going to be negative cotangent x cosecant x. And that's it. The fourth one here, this one's a little bit more complicated. Actually, I'm going to get a little more space down here. Let's see. Let's grab these. And put them down here. Okay. So this fourth one, we'll say y prime. So we have a quotient, and inside the quotient we also have a product. So in the numerator, x squared times cosine of x, that's a product. So when we take the derivative of the numerator, we need to use the product rule. Okay, so the derivative of a quotient, we do the derivative of the numerator, and again, that's a product. So to find the derivative of this, I need to do derivative of the first, so 2x times cosine x plus x squared times the derivative of cosine x is negative sine of x. So that all is the derivative of the numerator times the denominator, sine of x plus 1, minus the numerator times the derivative of the denominator. So the derivative of sine of x plus 1, that's just cosine of x plus 0. Don't write plus 0. And then it's the denominator squared. So we can probably do a little simplification here. In this spot right here, I can multiply that out pretty easily. We're going to have 2x cosine of x minus x squared sine of x. And then we could multiply that all out by sine of x plus 1. We'd have to do some distributing. I'm not going to worry about that. And then this back end, I have x squared times cosine squared of x all over sine of x plus 1 squared. So that's good enough. If we wanted to, or were asked to simplify further, we could multiply all of this together, but that's going to end up with 4 terms. Yeah, I don't think we want to do that. So that's good enough. All right, and then this last one, we have y prime. Okay, so the derivative of tangent of x, that's secant squared of x, plus the derivative of cotangent of x is cosecant squared of x, minus, now taking the derivative of this is where things kind of get complicated. Because again, now I have a product, but it's in the denominator. So this is a quotient. To get the derivative of a quotient, I do the derivative of the numerator. I'm going to put this in brackets here. 3x squared, just using the product rule, and then times the derivative of the denominator, tangent x sine of x, minus the numerator times the derivative of the denominator, and the denominator is itself a product, so we need to use the product rule to get the derivative of tangent of x sine of x. So the derivative of the first factor, the derivative of tangent, is secant squared of x times the second plus the first factor times the derivative of the second factor, so cosine of x. Okay, and that all gets divided by the denominator squared. And another bracket here. All right, so that's good enough, but let's simplify a little. Secant squared of x plus cosecant squared of x. All right, so I'm going to keep this minus in front. I'm going to have 3x squared tangent x sine of x. And then minus, we'll have x cubed secant squared x sine of x minus x cubed tangent x cosine x, all divided by tangent x sine x squared. And then we can distribute this negative through. And what I'm going to do is I'm just going to, when I distribute that negative, this becomes plus and this becomes plus. And then I can erase those. So I think that gets it for us. Hopefully all my signs are correct. If it's wrong, put a comment in the down there in the comments. All right. So let's look at a couple more examples. So we did all those ones. Higher order derivatives. So something kind of interesting with the sine and the cosine derivatives is that they're, you can think of them as periodic or cyclical, because we'll see that there's a pattern here. So y prime, that's just the first derivative of sine of x, so that's cosine of x. Y double prime, so now I want the derivative of cosine of x, so that's negative sine of x. Then the derivative of negative sine of x, well, the derivative of sine of x is cosine of x, but if I want the derivative of negative sine of x, that's negative cosine of x. And then next, the fourth derivative is just the derivative of negative cosine of x. Well, the derivative of cosine is negative sine, so the derivative of negative cosine is positive sine. And we notice as we're right back to where we started. If we keep going, if we take the next derivative, we get cosine of x, and then negative sine of x, then negative cosine of x, and then sine of x. So we notice is that every fourth derivative, we get right back to where we start, and they just always repeat themselves. And for cosine, it's a similar idea. F prime of x, so the first derivative of cosine is negative sine of x. F double prime is going to be the derivative of negative sine of x is negative cosine of x. Third derivative is sine of x, and then fourth derivative, we are back to cosine. So the derivatives for sine and cosine repeat themselves every fourth derivative. So this example says this guy right here is the 78th derivative of cosine of x. So what you want to do is we take whatever number derivative we're looking for, and we divide by 4. So 4 goes into 78 one time, you know, remember how to do long division, bring down the 8. 4 goes into 38 9 times, 36. I have a remainder of 2. So the remainder of 2 just means, well, I'd go from 1, 2, 3, 4. So if I have a remainder of 2, that means I look at this one right here. So the 78th derivative of cosine of x is, let's see, I can write it like this, d78y dx of cosine of x will be negative cosine of x. So it's just kind of a cool shortcut to find these higher ordered derivatives. Okay, last two examples here. Example 4 says, let cotangent of x be our function. Determine the points on the graph where f of x, determine the points on the graph of f of x where the tangent lines are parallel to y equals negative 2x. All right, so one thing to think about here first is maybe to remember what the graph of cotangent of x looks like. And cotangent of x has a period length of pi, and tangent of x is a decreasing function. And then we have asymptotes at pi. Okay, so I also have an asymptote at negative pi. Something like that. Also have an asymptote at 0. So it just keeps repeating. Now what it's saying is determine the points on this graph where the tangent lines are parallel to the line y equals negative 2x. Well, the line y equals negative 2x is, I don't know, something like that. Has a negative slope. And actually our slope is negative 2, so m is equal to negative 2. So what we want to know is where are the tangent lines? Where do the tangent lines have a slope of negative 2? Well, it probably looks like it's something like around here. That looks like it's going to be pretty parallel to what we have. So we want to know what is that point. So to find the slope of that tangent line, we find the derivative of the original function. So f prime of x, the derivative of cotangent is cosecant squared. Okay, and we want to know when is that equal to negative 2. So we need to solve this trig equation. Cosecant is 1 over sine squared, or cosecant squared is 1 over sine squared. We want that to be equal to negative 2. If I take the reciprocal of both sides, sine squared of x is equal to negative 2. And I forgot something here. The derivative of cotangent is negative cosecant, so this should be negative here, negative here. And then I divide everything by negative 1. So I get sine squared of x, and I made a mistake when I was thinking about that negative. I'm trying to do this too quickly. Back up here, when I take the reciprocal of both sides, I get negative 1/2, and then divide everything by negative 1, I get 1/2. Okay, so to solve this trig equation, I'm going to take the square root of both sides. I get sine of x is equal to plus or minus square root of 1/2, which is the same as 1 over root 2, which is the same as plus or minus root 2 over 2. And depending on how you memorized your unit circle, maybe either of these is what you would be wanting to think about. Now, what this is saying is when sine of x, what angle, we're ultimately trying to find x here, and that's an angle. We're trying to say sine of what angle is equal to root 2 over 2. Well, if you can remember what the unit circle does, the root 2's are always right in the middle of the quadrants. So sine is root 2 over 2, that's when y is root 2 over 2, and that's at pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. So we have the positive ones here and here, and then the negative ones here and here. So we want to hit all of those values. So in other words, if we look back to where our graph was over here, the first one would be pi over 4, which might be something like right here. And then 3 pi over 4 might be here. And I guess that's true. We could see, looks like we have a parallel tangent line like right there. Okay. And then similarly, 5 pi over 4, if I did another cycle of that graph, I'd get 5 pi over 4 and 7 pi over 4. So my x values are pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, etc. But I don't want to be here for the rest of time listing out these values. So what we do is we can write a general solution here. So what I'm going to say is x is equal to pi over 4 plus the distance in between these values is 2 pi over 4 or pi over 2, right? Each time I'm adding pi over 2. So what I can say is x is equal to pi over 4 plus pi over 2 times k for any k integer. And all that means is if I put in an integer, k, it could be 0, it could be 1, 2, 3, 4, 5, 6. If I plug in that value for k, I'm going to get an angle that will solve that equation. And that makes sense because the cotangent graph goes on all the way to the left and all the way to the right. It goes on forever. So we have an infinite number of places where we have a tangent line that is equal, that has a slope of -2. All right, last example. Find the equation of the tangent line to f of x at is equal to secant of x at x equals pi over 4. All right, this is our good friend tangent line equation. So again, I take the derivative of the function. Derivative of secant x is tangent x, secant x. And I want to know what is that derivative, or what's happening at pi over 4. So you could graph this also to get an idea of what this looks like. Remember, secant is the reciprocal of the cosine graph. So there's my cosine graph. So my secant graph looks like this, and then like this, and so on. Okay, and we want to know at pi over 4. Well, cosine, there's 2 pi, there's pi. So pi over 3 is closer to pi, so this is pi over 4. No, what am I doing here? This is pi over 2. So pi over 3 is something like right there. So what's going on with the tangent line at that position? So that red line is your tangent line. So it looks like it has a negative slope. And so what this is saying is, what's the equation of that line? And it also looks like it has a positive y-intercept. So I need to first figure out what is the coordinates of that point. And I can put that into the original function. I could say f of pi over 3 is equal to secant of pi over 3. Well, that's just going to be the reciprocal of cosine at pi over 3. So cosine at pi over 3, I shouldn't put an equal sign here. Cosine of pi over 3 is equal to 1/2. So secant of pi over 3 is equal to 2 over 1, or 2. All right, so the coordinates of that point are pi over 3, comma 2. So that's my pass-through point. And then I want to know what's the slope of the tangent line at that point. So this right here is going to tell me the slope of the tangent line. So I'm going to say f prime of pi over 3 is equal to tangent of pi over 3 times secant of pi over 3. Tangent of pi over 3 is root 3 times secant of pi over 3. We already figured that out, 2. So this is 2 square root 3. All right, so we have all the information we need. We have the slope of that. Well, that doesn't make sense. Negative. Our slope should be negative. Why do I have a positive value? Maybe my graph is wrong. Secant. Let's see. Derivative of secant. That is tangent x, secant x. Secant at pi over 3 is 2. That does not make sense. It should... I hope you figured out where my error is. Here's the error. This red line that I drew is hitting the cosine graph, not the secant graph. So my red line, don't want to do that. My red line, see if I can erase. No, I can't. We want to get rid of that red line. That red line is on the cosine graph. I'm not going to get a very high rating on my YouTube video. So we want our line to be up here, because now that pink line is actually on the secant graph. And that makes sense too, because this can't be 2 here, because the highest point for a cosine graph is 1. So if it's 2, it's got to be above there. So that's wrong. Oh, hopefully you can forgive me. So we have our pass-through point, pi over 3, comma 2. And we have our slope, which is 2 root 3. So put it all together, and I'll write it in pink. Y minus y sub 1 is equal to m 2 root 3 times x minus pi over 3. So again, you can keep it that way, or you can move that 2 over, 2 square root 3, x minus pi over 3 plus 2. Or, again, if you want to impress your friends, you could write this in slope-intercept form. We don't want to do that, though, because then we have to add pi's and non-pi's and radicals and things. So we'll just leave it like that. So this is our line.